Well, yes, I find that extremely soothing, actually, because it is a kind of sort of formidable task of grasping this. It makes me want to retreat into trivial questions like, is this idea of predicting backwards going to put astrologers out of business?
Nothing will put astrologers out of business.
Well, alas.
Well, that certainly added a touch of lightness to these tremendous issues that we are discussing: infinity, black holes, and imaginary time. And at this stage, let's relax a little bit and have a bit of fun with mathematics at their most abstruse. I'm going to ask Arthur Clarke here to do some doodling with his computer and with a fascinating exercise with complex numbers, which is called the Mandelbrot set. Now, this is named in honor of a French scientist working for IBM. It's a mathematical equation which leads us towards the infinite. In effect, it makes the mathematics of the universe visual and incredibly beautiful. This is what we would see if we had eyes to see it, when order meets chaos. This is what's going on in the universe every day. An ordered universe is breaking down and becoming more disordered. This is the second law of thermodynamics in action, what Stephen Hawking calls Murphy's Law. Now, Dr. Clarke, you've been using your computer back home in Sri Lanka to explore the Mandelbrot set at incredibly high magnifications. Over to you, sir.
Yes, well, this strange-looking object is the Mandelbrot set, which actually is extraordinarily simple in concept. It's defined by an equation of just two terms, z squared plus c. That's all there is to it. Yeah, that simple equation, z squared or z squared plus c, you feed a number into it, then carry on over and over again, sort of cranking the number back round and round, and then plot the result on the screen. So I won't go into details, but this is the first appearance of this set. And what it does, it divides all possible numbers into two categories. It's really a map or a boundary or a fence, if you like, dividing one class of numbers from another. And you can tell your computer to go into any spot here and say, recompute that area to a higher degree of precision, and then blow it up on the screen. So you can use the computer as a microscope, and you can continue that process forever. Some of the images are incredibly beautiful and are going to have a great impact on artistic design in the next decade or so. I found what looked like black holes, and I'd like to show them to you. So what I'm going to do now, essentially, is to zoom into it, increasing the magnification manyfold, and if I press the right button, it should happen now. The computer will now give you this image, and I think you'll agree when it comes up, it's a very impressive black hole. And it'll be even more so when I start it into action.
Oh yes, it is magnificent, isn't it?
You ain't seen nothing yet. I should explain that this magnification, you remember the original picture which it took about the same area, this time I've magnified it about 1,000 times. So the picture you saw first is now 500 feet across. Now let's see if this works. Now, isn't that lovely? So there is matter streaming into this black hole. Well, now, when I found this black hole, I started exploring the neighborhood, and I very quickly found another.
Indeed.
Now this...
That's lovely.
Now this is the second black hole. Now it looks just like the earlier one, but this is on a far greater magnification. The original Mandelbrot set now is, I think, about 10 million miles wide. This is enormously bigger than the first one you saw, yet essentially it's the same kind of pattern. This is black hole number 3, and this one took me 22 hours of computing the day before I left Sri Lanka. I had the computer running all night, and I'm rather proud of this one because on this scale, that original little picture you saw is the width of the orbit of Mars. So you understand that no human being has ever seen that particular pattern before, simply because of probabilities. And you can explore the Mandelbrot set by blowing up bits and pieces of it, and you can be pretty sure that no one's ever seen that. You're the first person to see it.
And each time you're being drawn towards...
You're being sucked into it.
Mathematical infinity.
Into smaller, and yes, this is real mathematical infinity. This goes on forever and ever, limited only by the capacity of your machine and the speed with which it can do its calculations. I am doing calculations here. You may not be able to see that enormously long number, the 20-digit numbers or so, and the machine is multiplying those together hundreds of times a second. Now, the thing that fascinates me about this is that it is infinite in detail. You can go on forever and ever. Now, I would like to ask Stephen this question. Is the real universe also infinite in detail? I mean, we know we have molecules, atoms, electrons, protons, subatomic, right down to the quarks so far. But does it continue forever and ever? Or is there a limit? Is there a basement to the real universe?
Professor Hawking.
We will discover new structures when look at the universe on smaller and smaller scales. But in the case of the universe, there seems to be a limiting scale. It is called the Planck length, and it's about 1,000,000 billion times smaller than an inch. This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length. I just hope that we are smart enough to find it.
Are we smart enough to find it, Arthur?
Well, I wonder, because after all, we're still pretty primitive organisms, and the universe is very old. And I just don't know. I would like to think so, but then there's a feeling, when we found it, then what? Where do we go from here?
I'd like to turn our attention back now to Professor Stephen Hawking. Do you think that we could ever hope to use the old science fiction trick of diving into a black hole and then traveling to another part of the cosmos?
Some recent work indicates that particles that fall into a black hole can come out again from another black hole somewhere else in the universe. At first sight, this seems the ideal method of space travel. Just find a black hole and jump in it. But there are snags. First, there doesn't seem to be any way to choose where you come out. Worse than that, your history in real time would come to a sticky end, as you were torn apart by the gravitational fields inside the black hole. Your history in imaginary time would continue out of the other black hole. But that might not be much consolation to someone being made into spaghetti. It would be like traveling on some airlines I could name.
So how do you see the actual role of science fiction? Is it purely escapism, or do you see it as having a very real purpose in broadening our patterns of thinking, opening our minds to the kind of vast concepts which we're discussing today?
Well, first of all, there's